Today we'll talk about object-oriented programming, which is pretty much a computer science area, but we'll put it in a very useful physics example. And so it'll give you some good ideas about what object-oriented programming means and how it's used. First, we'll talk about simple object-oriented programming. More advanced objects we'll talk about later, and they're certainly in the text, and I recommend you read the text for the more advanced concepts. Many people who don't know anything about object-oriented programming find it very hard to get going. So we've done a number of things to get you going more easily, and that's what this discussion will be about. I should say that the text, while it uses some object-oriented programming, uses it very mildly and stays more or less within the procedural programming techniques that are more common in Fortran and C. That's not to say object-oriented programming is not important. It's very important in computer science, and there are other books that actually spend more time presenting everything in a pure object-oriented method. We won't do that, in part because we want to keep things very similar to the mathematics, which procedural programming is, and also not have too much focus on something new in computer programming. So before we get going, though, we should say object orientation and object-oriented programming has become a buzzword. You hear business people using it, you hear commercials using it, and many people get turned off or confused because they don't know what objects are. Let's just say you're familiar with objects already from your study of even elementary physics. When we speak about something like a vector, velocity, position, with multiple components, that's really an object. What we mean by an object is something that has multiple parts that you have to deal with, but you're represented by one symbol. Once you think of that, think of objects as similar to vectors, you won't have any trouble. Okay, so here is the problem. The problem is a standard problem from elementary physics. We have an RLC circuit. That's, in other words, a circuit with a resistor. In this case, I've given you some numbers, and they're designed to make life simple for you and me. An inductor L and a capacitor C, all in series as shown in the pretty yellow figure. And the problem is we're given an AC voltage that's applied to the system, and you're asked what is the current that results. And of course AC means alternating current, and if it's a voltage it should be AV because it's alternating voltage, but such is life. Everyone calls it an AC. Okay? And so the voltage varies like the cosine of omega t. Omega is the frequency of the external source here, and a little wiggle means it's a sinusoidal source, and omega can vary, let's say, between 2 and 0. Okay. So the mathematical technique we'll use to solve this problem is complex numbers. And complex numbers are very useful in math and science. They make life very simple. They essentially double the work output that you can get from your hard work with just the slightest increase in input. That's what makes them so valuable. You do your mathematical manipulations much the same as you would with purely real numbers, but then when you're done, you separate off the real and the imaginary parts, and you get two separate answers for the price of one. So that's why in many cases they are very useful. Plus they make the notation very simple, and sometimes you get very complicated answers at the end without ever having to deal with the complications. So that's exactly what we'll see today. Okay. The whole basis of imaginary numbers and complex numbers is the imaginary number I. So I here is the square root of -1. That means if you square I, you're left with -1. A number like that doesn't occur in the real world. That's why it's called imaginary. Someone dreamed it up just to make life more simple. So a number I, or I times any other number, is a purely imaginary number. We deal usually with complex numbers, complex meaning not complicated, but with multiple parts. So a complex number has two parts. If we represent the complex number as z here, it has a real part x, called the real part of z, and it has an imaginary part y, called y, or the imaginary part of z. Now, strictly and semantically, some people get confused. If we have a complex number, its imaginary part is really I times y, because this is the real part. If it's an imaginary part, it has to be imaginary. But typically we'll say the imaginary part is just y and forget about the I, but strictly that should be there. Okay? And we often imagine a complex space in which x is plotted along the real axis, as on the figure here, y is plotted along the vertical axis, the y being the imaginary part of a number. And this is a space, in reality, we can only imagine because it's a complex space. It doesn't occur in nature. It just occurs in our imagination. Can you do computing with complex numbers? The answer is sure. We can do anything we want. It's a free world. Okay? In Java and C, however, the primitive data types, in other words, the kind of data that are built into the programming language without you having to do it yourself, are things like doubles, floats, integers, not complex numbers. It may change in the future. Many scientists say Java is good for programming. Let's have some complex numbers. Fortran, in contrast, has complex numbers built in. That means you just use them. You can even take sines and cosines of complex numbers. Fortran knows just what that means. So we will construct complex numbers in Java, for the example here, as objects. So our objects today, let's go back to how we started, our objects will be complex numbers. And they're like vectors in the sense they have several components, several parts, but we think of them as one number. How do we do this in Java? Well, first thing we need to know is some more mathematics. How do you deal with complex numbers? What's the arithmetic of complex numbers? So take a look here at slide 4. Slide 4 shows the arithmetic for complex numbers. It shows us how to add numbers, how to subtract numbers, how to multiply complex numbers, how to divide complex numbers. I won't go through the details here, but certainly you might be encouraged, if you're not familiar with all this, to stop the lecture right now and just stare at the slide for a while. Make sure you understand. Particular, it just takes the real and imaginary parts, multiplies them. Division gets a little more complicated. It uses the complex conjugate. So as we show on the bottom of slide 4, complex conjugate takes a complex number and reverses the imaginary part. And we can use that to get the modulus of a number. So this is the arithmetic we have to build in. Usually the people who write compilers build in all the arithmetic rules when you have the multiplication, division, symbols, so forth in the language. Here we have to build it in ourselves. So this is like building our own language. Okay. As I said, the valuable part of complex numbers often is to view them as a plot, as a vector in space. This is called the polar form of complex numbers. So we imagine, as we see here in the figure in red, a vector in complex space. It could be two-dimensional space here. The real part along the x-axis, the component, its y component, is its imaginary part. So once we think of that, we have the polar representation of complex numbers. The length of the vector r is just given by the square root of x squared plus y squared. The x component is just r times cosine of theta, as any other vector, and the y component, or the imaginary part, is just r times sine theta. And the angle theta here, called the phase of the complex number, is just given by the arctangent function of the y component, vertical, over the horizontal x. Euler, this incredible mathematical genius, said, you know what? If we raise e, the base of the natural log system, to an imaginary power, I to the theta, it must be equal to cosine theta plus I sine theta. Now that's not obvious. If you expand it, you can prove it, and I won't prove it here, but that's very useful for the work we'll do. So that lets us write a complex number either as x plus iy or as r e to the I theta. So this polar representation is given explicitly in one compact form, and the two are related. And we'll do this on the computer. The textbook carries this even further and writes methods for converting between the two. But this is the basic mathematics. So now you need to understand this mathematics. So you should go out, get some exercise. Stop whatever else you're doing. Take these two complex numbers, complex because they're real and imaginary parts, and do some arithmetic on it. Okay? If you know how to do this, there's no question, go ahead. If you don't, stop the lecture, go ahead, work this out, make sure you understand the rules, because the computer can't understand it unless you tell it how to understand it, and then we'll go ahead and do our thing and put this on the computer, then have the computer do it. So, get to work now for a while. I'll have some tea. I assume you've worked out all these problems in one fell swoop, and we'll just go ahead now, talk about doing some more things. Okay, how do we solve this problem? We have our circuit here, our RLC circuit, alternating voltage source, and we need to solve the problem. And the basis is really energy conservation, as a physicist would say, or as an electrical engineer would say, Kirchhoff's voltage law. So we just say the voltage source, V, must be, that's what you're applying to the whole circuit, that must be equal to the drop in voltage as we go around a loop. It's a series circuit, it's very easy to do. So the sum of all the voltage drops is equal to the voltage source. If we apply that law to this circuit, we get equation 2. Now equation 2, to be fair, if we apply the law, we get the voltage drop across the capacitor involving the charge on the capacitor, and that gives us an integral differential equation to solve, which looks terrible. So what we've done here in equation 2 is we've simply taken the derivative with respect to time of Kirchhoff's law, so we get everything in terms of current. So the voltage is known as a function of time. The current we have to solve for, so we have a second order, right there's a second order, differential equation. It's linear, but first power of I. They're easy to solve. Okay. But now we say, let's look at this and see if we can figure out a nice quick way to solve it. And we say we know the input voltage on equation 3 here is just V0 cosine omega t. But wait, that's just the real part of e to the minus I omega t times V0. Now, it could easily be plus I omega t. And in engineering classes, you might have plus I omega t. Physics almost always uses the minus sign convention for the time. Doesn't matter. Sometimes your engineering class would use J rather than I for the complex number as well. It's just a word. We're using I. J would work equally well. Okay. So what I just said before, the important part is we know the voltage for our circuit is the real part of this complex number. But since we have a linear equation to solve, we could solve this for a complex current and just take the real part or the imaginary part separately, and it's like two solutions. So then we're saying, okay, let's try to be clever. Let's guess a solution. If the voltage varies like e to the minus I omega t, on equation 4 here, we say, how about guessing that the current also varies as e to the minus I omega t? Now, of course, this would be a complex current. You can't measure complex currents in the laboratory. So what we mean, and we do it without saying, we should say it, I guess, but a lot of things we should do. We mean that the current is really the real part of this imaginary, complex current, rather. And then when we're done, we'll just take the real part to get the answer. So if we make this substitution, if we substitute this current into the differential equation, equation 2, we get a solution. We find that the current as a function of time is given by some constant, 1 over z, times the voltage, times e to the minus I omega t, or if we multiply by z, this is just saying the voltage is I times z. So, where we've usually had resistance in Ohm's law, V equals IR, we now have resistance becoming impedance. So Z is called the impedance. So you have an AC circuit involving more than resistance. We still have Ohm's law, but we have an impedance rather than a resistance. What we see here is we have an R, an L, and a C in parallel, and the impedance just adds for each of these elements. So the resistance, R, just gives us an impedance value of R. The inductor, L, gives us an impedance value of I times 1 over omega C, omega being the external alternating voltage, C being capacitor, and L, the inductor, gives us an impedance of I times minus omega L. So they have an impedance, a resistance to current flow, which varies with the frequency and has a minus sign, which indicates in this case whether it leads or lags. But we'll see. So this is the analytic solution to our problem. Good. So now we'll take a break. Look at look at slide 8 for a moment or two. Enjoy the beautiful abstract artwork. Okay, so on the left you see this beautiful piece of abstract art. When you look at it, what do you see? Well, some of you may see an artist's rendition completely lacking in artistic ability, and I apologize for that. Others of you may see something else, and the answer you get when I've asked this of students in class tends often to be gender related. So some of you will look at this and see a human figure in profile, if that's what you have on your mind. Others of you will look at this and see, oh, that's a human face. Okay? Well, this is abstract. It tries to be abstract art in the sense that it's an object that suggests more than what's given. So you see your mind's eye fills in what's there. So abstract, sometimes called formal concepts, pervade much of mathematics, science, mainly because they make things easier for us. We can do manipulations, we can understand in very compact forms what would otherwise be very complicated. They have many different forms. Let me give you one example. Ordinary velocity. You've probably seen that in your elementary physics class, and you'd say, no, velocity is not an abstract concept. I can see velocity. The answer is no, you can't see velocity. If you look at an object, you can measure its position. You can measure its position at another time, and you can see that position's changing. Your mind infers that if the position's changing, the object must have a velocity. So velocity is abstract. You don't measure it directly. You measure a change in position. You do some mathematics to deduce what the velocity is on the speedometer, say, but actually it's measuring positions. When we speak of abstract objects in computer science, and an object, the object in object-oriented programming is an object, it's an abstract object. When we speak of abstract objects, we mean a symbol we use to represent a data type that has multiple parts. It's as simple as that. It's just something with a lot of parts we represent with one symbol. The primitive data types, as we've said, things like doubles, ints, they're easy, floats, they're easy to manipulate. Objects, abstract objects, are just as easy. But we have to build them up ourselves by using these primitive data types to generate something more sophisticated, more abstract. Okay. Another term we have to discuss is class. Recall Landau's first rule of education? Most of education is just learning what the terms mean. The ideas are pretty simple. This subject is full of terms, and the people who know the terms intermix them, use them in sort of abstract new ways themselves, just to make it confusing to you. So I'll try not to do that too much. So an object, we've already said, is just something with multiple parts. A class is often used to represent an object and its different parts, along with the data that makes up the object or that the object works on, along with the methods which manipulate the objects. So when we speak of a class, we're speaking of all the objects and everything you can do with the objects. In computer science, in these computer languages, you know objects already. Complex numbers are an example of objects. Plots, graphs are actually objects. They have lots of parts. You want to manipulate them all. Matrices is an obvious thing because it's made up of many elements. Okay. We often speak of an instance of an object, and that means an object with specific values given. So a complex number is an abstract idea, which is an object. But if you actually give values to those numbers, to the real and the imaginary part, you still have an object. It's just called an instance of that object. For example, down below here at the bottom of slide 8, if the complex number, real part of z, imaginary part of z, is an object, it's still abstract. It's not a number until we give it values. Then we give it values, it's a real number. 2 plus 3i, that's an instant. Okay, so let's go ahead and look at slide 9. Slide 9 formalizes what we've just been saying. Even before this emphasis on complex objects, we always had abstract data types in computer science. And an abstract data type has 3 properties in order to be called abstract, and it's good to review them now because it makes you understand what we've been trying to say about objects. Okay? First, it has to have a type name. In other words, we start with elementary pieces, we define some new object, we have to give that object a name so we can deal with it. Once it has a name, it secondly must have a way of getting values to that object, set values. So that's the mechanism. Okay. And then once we have an object and we can give it values, we have to do something with it. All this talk is worthless unless you get something done. Okay? So we have to have functions, or methods as they're also called, to do the operations. So these are the rules of operations. So for example, let's say we have a complex number, z, x plus I, y. We would declare it, in other words, give it a type name by saying, in quotes here, to say that this is what we'd enter in the program. We'd say complex z. We would know, and we'd have to tell the computer somehow, that that means it has a real part and an imaginary part. We would then assign values for its real and imaginary part. That's how we set values. And then we must also have operations, and that's that big slide I gave you, additions and multiplications. We have to build that in. So that's how we define a formal computer science abstract data type. How do we do this in a program? So you know how to do this. So let's look at slide 10, and slide 10 just mainly reviews things you know already and the slightest addition. How do you start a program? You always start a program, particularly if you do it well, okay, by declaring the types of data you have. So for example, you might say double x. That's just a declaration. Doesn't assign a value to x, it's just telling the compiler x is going to be a double precision variable. Okay. The rule, and even if you're a Fortran programmer, we don't have to, but you should, follow the rule, is that every variable you use in your program must be declared. It's good for you, it's important for the compiler to know that. As we've said, the built-in data types you can declare a double float int. What's new here is if you define a new data type, an abstract data type, an object, you declare it exactly in the same place of the program, exactly the same way as the primitive data types. So you might say complex z, where I've defined complex to create the objects and make them the way I want. Okay? So this creates the object. Here, when we declare it, these will be dynamic data types. And dynamic means non-static. And non-static means there's not the word static used in front of them. So recall in a lot of the Java programming, we always had these, public, static, blah, blah, blah. Well, the static meant they were not objects. Java is really an object-oriented language, so if we leave off the word static, what's there is by definition, by default, an object. It's dynamic. What we mean by dynamic will become clearer, but it means you can do more with it than you could with a simple scalar or static variable. Okay. When we talk about methods, so objects are all, are dynamic always. The methods that deal with these objects could be static or dynamic. You have a choice of both. In the text, I mainly emphasize static methods just to make it similar to the C and Fortran programs. But you're free to go beyond that and learn more dynamic methods, and we'll give you examples of both. Okay? So the static method is like ordinary mathematics. You have a function or a method, and it takes a argument, z. Z can be an object, complex number, and that's fine. That's a static method. Okay? A dynamic method or non-static method would actually modify the object. So if z were the object, you can think of it, like I'm adding something to it, like a vector, like taking a dot product or taking a cross product. I'm making it do something. So this is how this sort of like subscript, this dot operation, modifies the object dynamically. Okay? So dynamic objects incorporate the most powerful aspects of object-oriented program. They're good to do, but they are both very powerful, they're very compact, and unless you're familiar with it, you may get confused. It's hard to learn at first. So we'll show both. So let's go on to slide 11. Slide 11 gives you a program using complex numbers. So take a look through this 17 lines, and then we'll talk about each line. Okay, and I should say the program complex.java in the book has more items here than I could fit on the screen. So I've just taken some of these items out just to give you an idea of what the program's about. And I should also say, I hate looking at code on a screen and have someone point at a code. I mean, you can't look at all this and understand it all at once. So you need to sit back and say, what am I trying to understand? You're just trying to get the general picture. Okay? So the details don't matter. You can turn the lecture off, look at the details in detail and slowly, and see how the pieces fit together. So let's, talk about the general view. So we start off here at the beginning. We say public class complex. Public means everybody in the world can look at this class. We're not restricting it. We're nice people, we should do these things. Class means, now something new, class means that this is a class file. And in the object-oriented programming sense, or OOP, this means that this class will have both objects in it, methods, and data. That's why it's called a class file, and it'll be stored either as complex.java when it's the source, or when it's compiled, it'll be complex.class, meaning this is a class file. That's what Java can work with. Okay? So we call it complex with a capital C because we always start off the class files with a capital C. But remember, that's important now. Now we have two class non-static variables we declare. So this is, the first brace means the class is beginning, and this means we'll declare these variables so every place in the class with all the methods can use these. And they're public, everybody can get to them. They're double, they're real, and imaginary are the two names. You can guess what they're going to be for, but they're declared to be just ordinary doubles. They're just going to be doubles, but they're not static. So these, by not saying static, they're dynamic, means they get associated with an object. You don't have to say that. That's essentially the default for Java because it's object-oriented programming. Then in line 3, we have our usual main method. Nothing there looks any different. But now we get something new. Line 4, we're saying A and B are now going to be complex numbers, and we declare them to be complex. So notice a couple of things here. One, we spelled complex with a capital C. It's not lowercase like double is. That's indicating that this is an object. Okay, so these are objects and they have capital letters. We'll also has the same name as our class file because we're making these, we're making everything here new complex. So this declares A and B to be complex. On line 5 and 6, we actually create the objects. Okay? So we say A is equal to new complex, braces, nothing there, and that says the compiler knows that A is complex, but it hasn't done anything about it. Now it does something. Now it makes it. So line 5 creates A to be a complex number. If we don't put any numbers inside here, this is now a method, as we'll see, that just creates the object with zeros automatically. Okay? On line 6 we say, let's do something else. Let's create this object B, complex number, with a real part of 4.7 and an imaginary part of 3.2. So we use the same method being called here, except now we put numbers in. That's it. And in line 7, we do, in one fell swoop, a new variable. We say the left-hand side of line 7 says complex C. And that's a declaration, just like we have here in line 4. And it says, make C a complex number. Okay. So the compiler knows that C is a complex number. And then on the right-hand side of line 7, we have create this object, new it means create the object, and make it a complex number with values, 3.1, 2.4. So that does the declaration and the creation all in one step. That's fine. You could do it that way. You could do it either way. Whatever you like is fine. Line 8 is just an output statement. And the only thing really new to notice in line 8 is, don't worry about these quotes. That's the usual strings in Java. But here we're printing out the real part of A. And the way we get to the real part of A is to say the object A, and we have this dot operation, extract the real part. And then we say, let's print out the imaginary part. We have A, the object, we operated on with a dot IM to extract the imaginary part. So that's new. Notice too that what I've done here is I've put in the main program, I put it at the top of this file. You can have the main program anywhere. Java doesn't care that we haven't said just what these complex objects are yet. Many programmers put main at the bottom. Okay, and there's, and I have maybe not put all the braces in here just to fit everything in, so don't worry about that now. But now we see two things. We see how we created these objects. So we had one object which was created with no argument. That's the default constructor. So anytime we have a new object being created, a new abstract data type, as required by the computer science rules, we have to have a method to construct it. So this on line 9 and 10 is known as the default constructor, and this says if I don't have any argument, then give the real part 0 and give the imaginary part 0. But look at this. We're saying line 9 says public complex. There's no number here. It's understood. The complex object is understood. And then we're saying the real part, which is just a double, as we see on line 2, is 0. The imaginary part is 0. That should be 0 point to be more precise, but we just make it look nice. This is called the default constructor because if you leave line 9 and 10 off, Java automatically will do this. If you declare an object and you don't say how, put any numbers in, say how to build it, Java will just set all its parts equal to 0. On line 11 and 12, we see the the full constructor where we say, okay, make the real part of the object x, which is part of the argument here, so you have to give it an x. Make the imaginary part of the complex number y, which is the second argument. And you might ask, isn't this kind of crazy? We have two methods in the same program with the same name. Doesn't Java get confused by this? Well, no, Java's pretty smart. It's smart enough to say they're both complex with a capital C, so you know you're defining an object with this, that you know they are constructors of objects. One of them takes no arguments, therefore it's default. The other one takes two arguments, therefore it's this method. You could have another complex method taking 3 arguments, say, as we'll do give you as an exercise, say to make a complex number in the polar representation. Java knows if it has 3 arguments, it can't be this method or that, it has to be another method. So Java's smart enough to do that. Finally, on lines 13 to 17, we have a complex method. And we say here public static, interesting, okay. Public static complex add. So this is a method, but it's a static method. So it takes arguments, and that's right. It takes a complex number A as one argument, takes a complex number B as the second argument, and then it does something. What does it do? Add should give it away. It adds them together. Okay. So here, complex is not part of the method's name. Complex is declaring that the output of the method or the function is a complex number. Public means everybody can get to it. Static means it's not fully object-oriented. It's just static. It's non-dynamic. Complex means the output's complex. Add is the name of the method. Takes 2 arguments, both of which have to be complex. Inside, all it does is add the real parts and add the imaginary parts together, and then it returns. To do that, it needs to have a temporary variable or a dummy variable, temp. So it declares temp to be a complex number. It then creates temp all in one line, and then uses the default constructor, and then it gives temp's real part to be the real part of A and the real part of B. Temp's imaginary part to be the imaginary part of A plus the imaginary part of B. Then it returns temp. So temp is a complex number gets returned. Okay? So this is the nice static implementation. Study this a while, particularly before we go on, because now we'll show you how to do exactly the same thing dynamically. So let's go now to slide 12. And I need more tea, so I'm going to take a break. You should study this. I've taken you studied slide 12 in some detail now. Slide 12 is also on the CD in the book, and this is another way of defining complex numbers. It's called complex dynamic, or DYN.Java. And the reason we gave it a different name, I would have preferred to call it complex, is that we wanted to have both programs on the CD, and if we had two programs with the same name, it'd be very hard to compile. You could mix it together. So, but you can think of it, sometimes people will just spell complex with a capital K to have another version of it, which is another way to do it. But this is the same thing. This does dynamic methods. So we have 18 lines here. Interestingly enough, that's one more than we had on the previous transparency. And that sort of is normal. These dynamic methods that we use are more powerful, they're more elegant, but they often will take a few more steps to write out. Okay? But they're simple steps and they're easy to change. So let's see what we have. Line 1 is the usual public class. So we just define the class, and there's the name, complex dynamics. Line 2 is the same. We're just defining class variables. In other words, all methods within the class can use real and imaginary. Fine. The main is exactly the same. And now we define A and B as before to be complex objects, dynamic ones. We have A on line 5 being defined with a default constructor, which will make it all zeros. B being defined with a full constructor, making it have a real and imaginary part of 4.7 and 3.2. And we have C being defined exactly as before, and being declared in one line, on line 7, having some value. So that doesn't change. Line 8 doesn't change. The new difference here is lines 9 and 10. So on line 9 we say C dot add B. My gosh. Well, it's obviously adding, and one of the reasons some scientists don't like object-oriented programming is it's not using mathematical expressions. It's more like reverse Polish notation on a calculator. It's more compact, okay? And this is very compact. So what this is saying on line 9 here is to say, let's take a complex object, C, let's add another complex object, B, to it, and let's give the answer as C. So C is our original object. When we operate on it, it's like a vector. Taking a cross product, you modify the vector. So now we modify this object by adding another object to it, B. That's what it does. And on line 10 we say, let's start with object C. Let's modify that object by multiplying it by another object, B. And we store the answer in C. Okay, so when you operate on an object, you change the object. Usually you form a new object, which is what we do here. And that's written very compactly in lines 9 and 10. So then on the rest of the code, we just say what the methods are. The default constructor, which as I said we don't need, it'll be automatic, but it's good to see, takes, it's not a dynamic method. It takes 2 arguments, creates the object. But then on line 13 to 18, we have the non-default constructor, and that does something new. It says we use a temporary variable here called answer or dummy, fine, declares it to be complex dynamic, and then it says the new answer has its real part to be the real part of this times the imaginary part of the other, times the real part of the other, minus the imaginary part of this times the imaginary part of other. Whew. Now that is, if you go back and look, that's the rule for complex multiplication. But what is this and what is other? Where are they even defined? Well, the way object-oriented program goes is you always know you're acting on some object. So this means the object I'm working with, the object I started with. Okay? And other means the object that's acting on it. So you start with this object, you work with some other object. In fact, you can leave off this, and Java will know, of course you have to be dealing with some object, that's this object you're dealing with, you can leave off this. We put it in here just because I'm a nice guy. Okay. And then the imaginary part of the answer is, again, just some multiplication of the first and the second object's real and imaginary parts, and addition, which we get there. And then we want to return the new object gets replaced, in this case by C, or C, we return the changed object. So that's still this object. Its real part is the real part of the answer, and its imaginary part is the imaginary part of the answer. So this program does the same thing as the previous one, but it does it with dynamic objects, and they're defined differently, and they're dealt with in a little more compact way. Let's solve our problem. Okay, so solving the problem is not that hard. Okay, so now you have to go to the lab, and we want you to solve the problem. So slide 13 here tells you the things we want you to do. It's not very hard because you need to understand these codes and then extend them. The way you understand codes is, of course, you look at them. You look at them carefully, and then you run them, and then you tweak them, you build up your understanding. You can write it from scratch, but it's easier to take something and change it. So, depending on your orientation in life, we want you to extend either complex.java or complex-dynamics.java, or both. I would recommend, if you really want to learn object-oriented programs, start with the simplest one, do everything, and then do the dynamic one. If you feel you're in over your head now, just stay with the procedural programming approach in complex.java. No problem. So take the code, which we've shown you and given to you. Now you have to add methods. Write your own methods. First to do subtraction, then to do complex conjugation, then to take the modulus, and then to get the phase, in other words, that angle theta in the polar representation of complex numbers. And when you're adding methods, I know, it's easy to sit down and enter all your keystrokes at once and then debug the program. Think, whenever you add anything to a program, you're making mistakes. You have to debug it. So if you add one method, debug that method, and then move on. Then at least the compiler's errors will be in just one place. If you get too many errors, it's hard to find where they are and it's hard to debug. So do it step by step. We tell you to do the complex conjugation before you do the modulus and the phase because you'll need that for your other methods. You'll need it for multiplication in particular. How do you test your methods? Well, you don't test your method by seeing if your problem is being solved. You test it on some simple cases, such as we give here in number 3, where you know the answers should be. You know that if you just add two complex numbers, the same number, you should get twice the answer. If you add a complex number to its complex conjugate, you should get a pure real answer. In other words, you should get an imaginary part which is 0 or 0 within the precision. Okay? And if you subtract a real number from its complex conjugate, you should get a purely imaginary number out, and so forth. Okay? So, do that. Sometimes you want to debug it. Try it first of all with Z as input. Use whatever you want. I'd say first use pure real Z, then use pure imaginary, then maybe 1 plus I, something you know the answer for. So that's the first solution. Okay, so get your program running, make sure you can extend it, and now we need to, on slide 14 here, solve our physics problem and use some visualization tools to do that. So look ahead of what we have to talk about in slide 14, and we're nearly done now. Okay. So slide 14 assumes that you have your program running, and we will solve the differential equation, equation 1. And then we'll look and see if this kind of circuit makes any sense, if it makes any physical sense. Okay? So we have equation 1 here. That's the differential equation we want to solve. we have an analytic solution given by equations 2 and 3. So we know for input voltage, which is sinusoidal, the real part of e to the minus I omega t, the current is 1 over Z, or Z, the impedance times the input voltage, and that now, using the polar representation, the current is V divided by the modulus of Z, modulus of the impedance, and the phase. Okay, so and that's the reason Z is complex, if you want. It says an RLC circuit not only gives you a magnitude of the current, but the current has a different phase relative to the time variation of the input voltage. The current has a phase. It's displaced from that. Okay, so that's the complex number. What we want you to do now is compute the current, plot its magnitude and the phase independently on a simple graph. Fine. And some of you, depending if you have a really soft-hearted instructor, may say that's all you have to do, that's enough, and then you've learned about complex numbers. To extract the real physics of this problem, and it's interesting in its own right, you should go ahead and do a two-dimensional visualization or three-dimensional visualization in the surface plot. So make a surface plot of the impedance, or better yet, 1 over the impedance, as a function of both omega and r. So it's a 3D plot. And look also at the phase, phi, as a function of omega, which is the frequency of the voltage source, and r, the resistance. The reason I ask you to do 1 over the impedance is that, obviously, equation 2 here, that's what tells you when the current's the maximum. And what you see here is, as a function of omega, you see that, oh, there's a maximum in 1 over the impedance, which means a maximum in the current. Yes, this is known as a resonance, and at some frequency you get the maximum current. This in fact is the basis of the early radios, how they would tune. They'd have an RLC circuit, and you'd vary the resistance or whatever until only one frequency would get tuned, the frequency you're trying to listen to. And that's because if you make this peak very sharp, you don't hear the other frequencies, you don't hear much of them, and you mainly listen to this one. So this was the super heterodyne tuning circuits in the original radios. Okay, and likewise we see the phase also goes through 0, and you should notice it's at the same frequency. Okay, so if something happens, that's a resonance. Okay. One of the graphs I'm not showing you, so you have to do your own, is now look at the frequency dependence of the complex impedance Z as a function of complex frequency, the real part of omega, and give omega an imaginary part. And what you'll see here is, there's also a peak, doesn't occur exactly on the real axis of omega, occurs on the complex axis someplace, and the imaginary part of omega is related to how long in time this resonance exists. So that really is the solution to our problem. What we'd like you to do is now extend the problem, finally, to say, what if we have 2 complex circuits, 2 RLC circuits in parallel? So look at slide 15. Here we have a circuit. We have 2 loops we can make. They're identical RLC circuits, and now we need to just generalize what you've done before. And the problem is compute the current in the total circuit here or in each individual part. Total circuit is just fine. Then you have to add the impedances together. So when the impedances are in series, like we have on each arm here, then they just add. But when the impedances are parallel, like we have here for the 2 separate arms, then they add in the inverse, just like resistors. So this is the problem for you to solve as an extension if you find you have too much time and the stuff is too easy. So that's all we have to say here for simple objects. If this is all too easy for you, go ahead, go on to more complicated objects. If you're having trouble understanding how the object orientation comes in here, stick with this for a while and maybe come back later. So we now will use object orientation throughout the whole book in various ways. Every time you call a math library, you'll see math dot something. That's object-oriented notation. When we do the plotting with PT plot, that uses object-oriented notation as well. So this is the basis for it. Now we'll use it. By the end of the term, it'll seem second nature to you. See you soon. Bye-bye.